So we're talking about our topic today. We're in, I'm going to call it 13.3, section 13.3. And this is the fundamental counting principle. And we're going to come up with, write a definition. The definition sounds complicated. It's like a lot of things we've done already. When you write it in words, it sounds complicated, but it's really not that complicated. And the fundamental counting principle, what we're doing, the reason that we're talking about counting is, like I mentioned at the very beginning, when we're talking about probability, when we're talking about our favorable things, our total things, we have to count them. Well, sometimes the things that we have to count are very difficult to count because there's so many of them. So we need to come up with a way to count a lot of things easily. So the fundamental counting principle gives us a way to count things. What the fundamental counting principle tells us is that if an event is just something that we're interested in, rolling a 6, type A blood, if an event can happen in m different ways, m is just some number, and another event can happen in n ways, together they can happen in m times n ways. So to figure out the number of ways that two things can happen together is we multiply. And if we have more than two things, we have to multiply more than two numbers. That's what the fundamental counting principle is telling us. It's just like on our game with our dice, where one die could come up 6 ways, the other die could come up 6 ways. We figured out that the total ways that two die could come up together were 36. 6 times 6 is 36. So we were using the fundamental counting principle. So let's take a look at an example of this and why it works, and then we'll use it for a couple of different things. So let's say that we have 3 shirts and 2 pairs of pants. So we have 3 shirts and 2 pairs of pants, and we know that they all match together well enough that we can wear them together. So we can combine them we can make 3 times 2 equals 6 outfits. And the reason this works, let me draw a picture here. So we have 3 shirts. So here are my shirts. I have shirt 1, shirt 2, and shirt 3. Well, shirt 1 I can wear, and this is the column for my pants. I can wear a pair of pants 1 or a pair of pants 2. For shirt 2, I can wear a pair of pants 1 or a pair of pants 2. And for shirt 3, I can wear a pair of pants 1 and a pair of pants 2. And if I count all my different outfits, I have 1, 2, 3, 4, 5, 6 outfits. So that's why this is why the fundamental counting principle works. For each shirt, I have 2 possibilities for my pair of pants. So 3 times 2 is 6. And we call this kind of diagram a tree diagram. The nice thing about the fundamental counting principle is it lets us count things that get big really fast without having to draw this tree diagram. Because some of the things that we're going to be talking about, you would have a huge tree with lots of branches. And to get them all written down and to count them all would be really difficult. So, any questions about what the fundamental counting principle is telling us? All right, let's look at another example of how we are going to use the fundamental counting principle. So let's say we need to make a password. We want a password with 1 letter and 2 numbers. And an example, let's say like our password is M63. So this is not a real secure password because it's pretty short. We want to know how many are possible. So we're going to use the fundamental counting principle. So for the letter, how many ways can we choose 1 letter? 26 different ways. The alphabet has 26 letters. So our letter can be, we have 26 ways. The numbers can be between 0, so a 1-digit number, so between 0 and 9, 0 to 9. For both numbers. I'm sorry? Right, so we want two separate 1-digit numbers. So for the first number, how many choices do we have? We have 0 to 9, so we have 10, right? So we're multiplying by 10. And for the second number, how many choices do we have? We can repeat. So our passcode could be like A00. So the number of possibilities is 2,600 passwords. Made from 1 letter and 2 1-digit numbers. What's that? 26 times, well, the reason I wrote it separately is because we have 10 choices for the first digit and 10 choices for the second, just to keep track of that. So how would this change if we wanted 2 letters? What would be different? We'd multiply by another 26, right? If we wanted another 1-digit number, how would it change? Multiply by another 10. You have another 10 possibilities of choices for the last letter. So these combinations get big really, really quickly. Because if we multiply this 2,600 by 26, that's a pretty good sized number. If we multiply this by another 10, we're putting another 0 on. So they get big, these numbers of possibilities get big really quickly. So if we wanted to draw a tree diagram for this 26 times 10 times 10, the first part of the tree would have 26 branches. For each of those 26 branches, you'd have 10 branches going off there, and for each of the 10 branches, you'd have 10 branches going off there. So this tree diagram for this password would be huge. The fundamental counting principle lets us simplify it and just write it as a multiplication problem. Now, before I talk about one other thing, let's throw a little twist onto this. Let's say that our password is 3 letters and 3 numbers, 3 one-digit numbers, with no repeats. How many possible here? So let's look at how we solve this problem. So we're going to start the same way. So for our first letter, how many choices do we have? 26. For our second letter, how many choices do we have? We've picked 1 already. We can't repeat it, so we only have 25 left. For the third letter, how many choices do we have? 24. We go down by 1. We pick 2 of them. We can't pick those 2 again. All right, there are my 3 letters. For the first number, how many choices do we have? 10. Second number, 9, 8. Someone have a calculator? Multiply this out for me. You do it already, Jordan? Like this?
Like 11 to
11,232,000 possible combinations. So this is similar to like a license plate with 3 letters and 3 numbers. So there are over 11 million possibilities of different license plates. Now sometimes there's more complications because the letter might have to the letters might have to start with a certain letter, and that would change things a little bit. But this gives us a good idea of how many possible license plates we would have and how big these numbers get really quickly. So is everybody good on fundamental counting principle, figuring out how many choices we have and multiplying to find the total number of possibilities? Yeah? All right, let's look at one other way of counting. And we get to learn a new math symbol. It might not be new, you might have seen it before. So I'm going to start this with an example. We're arranging 5 books on a shelf. How many different ways can we do it? So we're going to go back to the fundamental counting principle and figure out, I turned this off by accident. We're going to figure out how many ways we can arrange 5 books on our shelf. So if we have our 5 books sitting here on the table and we're going to put them on the shelf, how many choices do we have for the first book that goes on the shelf? 5. We have 5 choices. Once we pick that first one, how many do we have for the second? 4. And for the third? 2, 1. If we multiply these together, we get 120 ways. Now, this sequence of numbers, starting with the number and multiplying by everything down to 1, comes up so often that mathematicians made up a symbol for it and gave it a name. So we call the symbol is 5 factorial, this exclamation point, and we pronounce it 5 factorial. So anytime we start with a number and multiply, go down by 1 and keep multiplying until we get to 1 is called the factorial of that number. So 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. We can do 7 factorial, da 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 da. So blank factorial. So the way they usually write it in math books is n for some number. N factorial is n times n minus 1 times n minus 2. So we're just going down by 1 each time, times dot 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 until you get to 3 times 2. That's times. Times. We're multiplying. So all of these x's are multiplication. So we just start at the number and multiply going down by 1 until we get all the way down to 1. And it also doesn't matter which order we can put it in, or which order we do put it in. We could say this is 1 times 2 times 3 times dot 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 times n minus 2 times n minus 1 times n. I can put it in either order. Since we're multiplying, the order doesn't matter. And the other important thing to remember is that 0 factorial equals 1. Always. If 0 factorial equals 0, then we would run into problems. So we say that 0 factorial equals 1. So this calculation comes up a whole lot when we're doing probability. And we're going to do something on Friday where we're going to use factorials for calculations for all kinds of different things. So let me show you on a couple of different calculators. Your calculators will do factorials, and then I want to do one other example of factorials, and then we'll be done. So on our calculator, let me go to here. I'll bring this one up, and I'll also get just the regular computer calculator. All right, so on the regular computer calculator here, the factorial button is this one that says n exclamation point. So let me clear this and go back to here. And if your calculator has a button that has the exclamation point, I can say 5 and press that button, and I get 120. So the calculator calculates it out. 6, and I hit this, 720. 7 factorial. It's part of that. We'll talk more about that on Friday. But all the calculators calculating here is, I did 7 factorial, 7 times 6 times 5 times 4 times 3, and that's 5,040. I just want to show you how big they get. 8 factorial, 40,320, 9 factorial, 362,000. They get big really fast.
Skip all the way to 60.
60?
Yeah.
So 60 factorial, it might overload the calculator. So what this is telling us is 8.32, and this is times 10 to the 81st power. So there are 81 numbers after before the decimal point. So 81 numbers before the decimal point. So this is a huge, huge, huge number.
Would the graphing calculator do that?
We'll see. So on these Texas Instrument calculators that a lot of you have, there's a button that says PRB. That's your probability button, and that's a menu. And your factorial is in that menu. So let me show you. It's kind of similar on this big calculator. So I'm going to go to the I'm going here to the PRB. This one doesn't have a PRB button. It's a PRB menu. So I'm going to go over here to PRB. And then number 4 on this calculator is the factorial. So if I want to calculate 60 factorial, I'm going to go 60. And then I go to my PRB button. Go over here. Down to the exclamation point, the factorial, and I hit enter. So there's 60 factorial. So it gives us the same thing, 8.32 times 10 to the 81st power. If you're not sure how to use it on your own calculator, I can help you out with that. And we'll work more with doing calculations, factorial calculations on your calculator on Friday. Okay? And let me show you one other thing with factorials, just so you've seen it. This won't be part of the homework tonight, but we'll do this on Friday. What if we want to calculate something like 7 factorial divided by 5 factorial? Now you can put this in your calculator and figure it out. But the nice thing about factorials is the way that they work, they let us cancel things out really easily. So I'm going to rewrite this as 7 times 6 times 5 times 4 times 3 times 2 times 1. And we're dividing by 5 times 4 times 3 times 2 times 1. What can I do with this and this? What is it? I can cancel them out. It's the same on the top and the bottom, and I'm multiplying, so I can cancel this. And the answer is just 7 times 6, which is 42. So when we're dividing factorials, if you write them out, you can cancel things out, and it turns into usually turns into a really easy multiplication problem. All right, questions on factorials? We'll work with those more tomorrow. I just wanted to do an introduction today. Okay. Stop this.